Hello my dear student, today I'm going to talk about sum and a product of measurable functions. Okay, so if you have two functions, they are measurable, then their sum is also measurable. Okay, if you have two functions, they are measurable, their difference is also measurable. Okay, so if you have two functions, they are measurable, their product is also measurable. So this is going to be done in a theorem, okay, by establishing a theorem. Okay, so theorem is like this: let f and g be real valued measurable function. Okay, real valued measurable function defined on the same measurable set E. E may be R, E may be any measurable set. Okay, the domain of definition of f and g, they are same, E. Okay, so then f plus g, f and g are two functions, f plus g is a new function. Okay, so f plus g, f minus g, and the product fg are also measurable functions. So in a way it is a, it is a method of constructing a measurable function from given to measurable function. So if you have two measurable functions, their product is also measurable. Okay, their difference is measurable, their sum is also measurable. All right, so here we are going to take only real valued function. Okay, not extended real valued function. In a corollary, just after this theorem, we are going to extend this result to extended real valued function. Okay, so for the time being, let us do for real valued function. All right, sum, difference, and a product of two measurable functions, they are measurable. Okay, so for a given real number, let us see step by step. For a given real number alpha, so alpha is any sort of real number, then you define set A. What is the set A? It is a collection of point x. What kind of point? Such that at that point you evaluate f of x and g of x, take their sum, and that is greater than alpha. So you take those point x such that f of x plus gx is greater than alpha. Okay, and that collection of point is your A. If we are able to show that this set A is measurable for every alpha, then this sum of two measurable function is going to be a measurable function. Okay, that is the main objective. Is why we want to show that this set A is measurable for each alpha. Okay, so then let us see the statement. So we know that this one, this is very easy. F of x plus g of x is greater than alpha implies that after transferring this gx that side, f of x is going to be greater than alpha minus gx. Okay, so from here, from this statement, what do you get? This statement you get. Conversely, if f of x is greater than alpha minus gx, by transferring this gx to this side, you are going to get this statement: f of x plus gx is greater than alpha. Okay, so that means it is very elementary thing, but this is important. Okay, so this implies this one, this implies this one, they are equivalent statement. Okay, they are equivalent statement, right? And this is going to be, this is f of x is a real number, right? Alpha minus gx is a real number. Okay, then f of x is strictly greater than alpha minus gx. They are different real numbers. So from real analysis, what we know, between two different real number, there are countably infinite, okay, there are infinitely many rational number between these two real number. All right, between these two real number f of x and alpha minus gx, there are infinitely many rational number, and rational number is the set of rational number is countable, and that can be enumerated in this form: r1, r2, r3, like this can be enumerated. Okay, so let r1, r2, r3 be an enumeration. Okay, be an enumeration of the rational number between f of x and alpha minus g of x. Okay, the rational number between f of x and alpha minus g of x can be enumerated in this way. Okay, r1, r2, r3, like this, up to infinity. It can go on. Okay, so next, if if f of x is greater than alpha minus gx, then you can take one rational number between this one. That rational number is such that f of x is greater than that rational number, and that rational number is still greater than alpha minus gx. Okay, then there exists a rational number Ri from this enumeration such that this is true. You can insert one rational number. Okay, so that means this statement can be broken up two statements. One is what? F of x is greater than Ri. Another statement is what? G of x is greater than alpha minus Ri. Okay, from here you will get this one. Okay, simultaneously, and conjunction and. Okay, simultaneously. All right, so this statement can be converted into a set by what? X such that f of x is still greater than Ri. Right, and this statement also can be converted into a set by what? X such that g of x is strictly greater than alpha minus Ri. So this statement can be converted into a set. This can be statement can be converted into a set, and this conjunction will be replaced by what? By intersection, set intersection. Okay, and the conjunction and will be replaced by set intersection. Now this statement implies these two statements with this conjunction for some real number, some rational number Ri. Okay, in that enumeration. Conversely, if this statement holds and simultaneously this statement also holds for some rational number Ri, then you will get this one. Okay, f of x plus g of x will be greater than alpha. All right, that means what? This statement is equivalent to these two statements. Okay, all right, so this statement is what? This statement is equivalent to these two statements. All right, so for some Ri. Okay, so for different Ri you will get such statement. All right, then therefore when you replace this by set, what do you get? This statement is another equivalent with the this one. So this statement can be converted into this set. What is x such that f of x plus gx is strictly greater than alpha. This is equal to a. So this is b. B derived from this one. Okay, what is b? B is the union. Okay, b is the union I running from 1 to infinity. Okay, x such that f of x is strictly greater than Ri. This is a statement, and this conjunction n will be replaced by intersection x such that g of x is strictly greater than alpha minus Ri. Okay, so for each Ri it should be okay. For each Ri such statement will be there. Okay, if this is true for some Ri, that is going to this that statement will imply this one. Okay, all right, if this is true, then for some Ri you will get these two statements. Okay, so therefore this will be union I running from 1 to infinity, and this set. Okay, now let us see here. This function, this function f is measurable, therefore this set is measurable. All right, for each Ri. And this function gx is measurable, therefore this set is measurable for each alpha minus Ri, for each real number. Okay, alpha is a real number, Ri is also real number, alpha minus Ri is another real number. So g being measurable, this set is going to be measurable. So it is intersection of two measurable set, therefore this whole set, this whole set is measurable. So you are going to get union of countable union of measurable set. Okay, countable union of measurable set is measurable. That means b is measurable. So b is exactly equal to a. Okay, b is exactly equal to a. Therefore a is measurable for its alpha. Okay, a is measurable for its alpha. Therefore the new function f plus g is measurable. Okay, so hence the new function f plus g is measurable. So what is the conclusion? You have a measurable function f, you have another measurable function g, their sum is a new function, and that is also measurable. So next, let us see what about difference. F minus g. So f minus g, you know, it can be written in this form: f plus minus g. Okay, f plus minus g. G is measurable. Okay, in the lecture 5 we talk about product multiplication of a measurable function by a constant is measurable. G is measurable. G multiplied by the minus 1, which is a constant, is also measurable, means minus g is measurable. Okay, this minus g is measurable, f is measurable, then their sum is measurable just by the above reasoning. Okay, f plus minus g is measurable. So what is f plus minus g? F minus g. So difference of two measurable set function is also measurable. Okay, so it completes. F minus g is complete. Lastly, let us talk about the product of two measurable function. Okay, product of two measurable function. So from algebra, you know, from basic algebra expression, what do you get? A plus b whole square minus f minus g, no, f plus g whole square minus f minus g whole square, their subtraction, you will get 4 times fg. If you divide by 1 by 4, you will get fg. Okay, so the idea is that if you are able to show that f plus g square is measurable, f minus g square is also measurable, then just because of this result, difference of two measurables function is measurable. This is going to be difference of two new function, f plus g whole square, f minus g whole square. Their difference is going to be measurable. Okay, this is going to be a measurable function. So this measurable function is multiplied by a constant, then the resulting function is also measurable. That means fg is measurable. So the whole thing is now the proof is over if we are able to show that square of a measurable function is measurable. So if you have a function, if its square is measurable, then the theorem is over. Okay, it is done. All right, so that is the thing. So it is sufficient to show that f square is measurable whenever f is measurable. So if we are able to show that one, since f plus g is measurable, f plus g square is going to be measurable. Since f and g are measurable, f minus g is measurable, therefore its square is also going to be measurable. Then it is done. Okay, so therefore let us now prove that f square is measurable. Okay, so now first let us take alpha less than 0. Then square of a real number is always positive number is always greater than any negative number. Okay, so this is going to be true for all x in the domain of definition. Okay, R. Suppose if the domain of definition is R, E is equal to R, this is going to be true for all value in R. Okay, therefore x such that f square x is strictly greater than alpha, it is exactly equal to R. Okay, and R is a measurable set. Right, R is measurable set. So whenever alpha is less than 0, this set is going to be measurable. So now let us take the remaining case when alpha is greater than or equal to 0. When alpha is greater than or equal to 0, what do you get? F square x is greater than alpha means this statement implied by what? F of x is strictly greater than root over alpha, and f of x it is strictly less than minus root over alpha. You will get this statement can be broken up into two statements, this one and this one. Okay, so this is true means this is also true and this is also true simultaneously. N. If this is true, both are true at the same time, this is true. That means what? A point is there such that f of x is strictly greater than root over alpha, and at the same time f of x is strictly less than minus root over alpha. What do you get? N means conjunction. So what you are going to get? You are going to get this one. All right, so now let us translate into set these two statements. Okay, from this statement what you get? X such that f of x square is greater than alpha, you will get this one is exactly equal to, this equivalent will be equal to x such that f of x, okay, is strictly greater than root over alpha, and this will be replaced by intersection. So x such that f of x is strictly less than minus root alpha. Okay, So you are going to get this one. Since f is measurable, this set is measurable. All right, since again f is measurable, this set is going to be also measurable. All right, so that is what this is in intersection of two measurable set. Therefore this is measurable. That means this set is measurable for each alpha, when alpha is positive also, negative also, 0 also. Okay, therefore this function is measurable. Okay, this function, and that means the square of a measurable function is measurable. All right, so that means what? F plus g is measurable. Let me explain again. F plus g is measurable, therefore its square is also measurable. F minus g is measurable, its square is measurable. The difference of two measurable function is measurable, just we have shown. Therefore this is measurable, and multiplication by a constant is also measurable, therefore this is measurable. Okay, so now we have proof product of two measurable function is also measurable. All right, so now corollary, I told you, let us extend the above result to extended real valued function. Okay, let us extend the above result to extended real valued function. Okay, that means the function can take values positive infinity and negative infinity also. So then we have to include, okay, we have to include those point x such that in the theorem there is no the point which give the infinity is not there. So since the function is extended real valued function, we can include those point which give you the infinity point. All right, so while doing so, this part may give you positive infinity, but this part may give you negative infinity. Then you are going to get minus infinity to minus infinity. That is not allowed, that is undesirable, that is undefined. In extended real number, that is undesirable thing. Okay, so we have to exclude the point where minus infinity plus infinity, or infinity minus infinity happens. Okay, those things, those situations we have to avoid. Okay, we have to exclude those points by including infinity, but we should take care about minus infinity plus infinity, or infinity minus infinity. Okay, so this situation we have to avoid. All right, so now let us see. Then we want to prove the sum of this extended real valued function f of x plus g of x is measurable. So for s alpha, this set must be a measurable set. Okay, for the finite case you get for the extended for the real valued function you get this one. Since it is extended real valued function, we have to include the point where infinity is also there. Okay, so then you have to include x such that f of x is equal to infinity. So in some example we have proved that x such that f of x is equal to infinity, this set is measurable set. Okay, from this measurable set, sum of the point may be may give you g of x is equal to minus infinity. So this thing you have to remove now, because I told you to avoid the undesirable thing, minus infinity or minus infinity plus infinity. So this set is also measurable. This set is taken out from this set. Okay, and difference of two measurable set, and this is ultimately this is measurable. So now let us another case is what? Minus infinity plus infinity 1. So suppose the function g will give you plus infinity. Okay, but the function f of x may give you minus infinity. So then you will get the minus infinity plus infinity situation, that is undesirable. Okay, so infinity part is okay, g of x is equal to infinity part is okay. From this part you have to take out those points which give you minus infinity part. So this is subtracted. So since f is measurable, this set is measurable. Since g is measurable, this set is also measurable. From this you have to take out those points which will give you minus infinity. Okay, so this whole thing is a measurable set. Okay, so by including these two set, this one and this one, you have extended the above theorem to the extended real valued function. Okay, so and this is the theorem today I want to discuss with you. And for the case extension, for the extension to the function f minus z, do for this is a homework for you. You try it and you upload in the WhatsApp your workout, and then take a screenshot and you can upload to the WhatsApp. I will check it. Okay, we'll discuss there also. Okay, so thank you very much.